Our presenter tonight, research meteorologist Dr. Mike Kaplan, knows the answer to the question in the title of tonight's presentation, is something wrong with the weatherman? He's here to show us and to tell us just how hard weather prediction is and why it's so hard. Please join me in welcoming him. Dr. Kaplan.
Thank you, Steve. I'm going to dim the lights just a little bit. Now, the first thing I want to say is I don't want anybody taking notes, which should make everybody very happy because I'm sure you don't want to take notes. But the point is, I want to take you through a journey in terms of what it takes to develop an advanced weather prediction model. And I want you to get a sense of the flavor of the mathematics and physics it takes to develop a model such as this. And what really matters here is not that you know the details of what I'm going to discuss, because there are going to be a lot of details that I'm going to put in front of you. But what really matters is that you understand what it takes to make a great weather prediction model and why it's such a difficult problem. Now, how many people honestly believe that weathermen are idiots? Raise your hand, don't be bashful, come on. I need to get a sense of this. Probably about half of the audience. You know, Willard Scott talking about a 125-year-old lady in North Dakota or something like that, right? All right, well, hopefully, as I go through the presentation, you'll have an understanding of why Willard Scott is not at all what weather prediction is really about. This is me. This is the title. In my presentation today, what I want to do is fundamentally cover what it takes to make a great weather prediction model that we can put on a computer and predict the weather with. Also, I want to go into some detail in terms of the basic concepts behind the weather prediction model when we put on a computer, basic definitions that are necessary to make this model work, the physics behind it, the mathematics behind it, etc., the basic assumptions of a weather prediction model, the equations and physical processes, and I want to demonstrate some of those in front of you. And I've never demonstrated these before, so I may end up having things all over the place, but I'm going to try. And of course, the basic computational requirements. And as you'll see, they're really mind-boggling. That's why computers are necessary to predict the weather. Of course, I want to talk about some of the major problems and limitations of a great weather prediction model. And if we have some time left over, I'll show you some examples of what weather prediction models can do, in spite of the difficulty of developing them. Now, basic concepts. If you don't get this, the rest of the presentation is meaningless. Fundamental basic concept. The state of the atmosphere can only be known in advance if the laws that govern the atmosphere can be quantified. We cannot predict the weather by sticking our hand out the window or just by looking at a single cloud. The only way we can accurately predict the weather is understanding the physical laws and mathematics that govern weather prediction. These physical laws are based upon the equations that describe fundamental fluid flow, whether it be flow over a wing of jet aircraft, whether it be flow in a wind tunnel, whether it be a very, very slow flow or very, very fast flow. The fundamental equations of fluid flow, Newtonian equations, fundamental equations of thermodynamics are what weather prediction is all about. Now, it's important for you to understand, and I'm going to go through the process of developing the mathematics, that these equations don't mean anything to anybody unless you understand some basic principles of calculus. And the very simple principles of calculus drive all of what weather prediction is fundamentally based upon. And that is that rates of change of variables are dominant in weather prediction models. You have to understand what a derivative is and what an integral is. And fundamentally, the most important concept, the atmospheric prediction depends upon knowing values of variables within a three-dimensional fluid at a later time. Hence, it represents a four-dimensional problem in mathematics and physics. Three spatial dimensions and time. It's very important that you understand that we're talking about four dimensions in fluid dynamics and thermodynamics. That's what a weather prediction model is fundamentally all about. Now, even to get the most primitive or basic understanding of weather prediction requires that we know something about fundamental mathematics. And there are about 1,000 questions we can ask right off the top of our head about mathematics that are appropriate for weather prediction. But there's some fundamental definitions that we really have to understand, or else we're not going to be able to understand what it takes to make a great weather prediction model. The most basic concept in weather prediction is the fact that there is a relationship between wind, temperature, pressure, density, and moisture, and space and time. Now, in fundamental calculus, there are two types of variables. One called dependent variables and one called independent variables. Independent variables are just that. They are independent. Space and time are immutable. They don't depend on anything. Everything depends on space and time. However, the fundamental physical characteristics of the atmosphere, wind, temperature, pressure, density, moisture, are dependent upon space and time. Now, the basic concept of all of calculus is the concept of a derivative and the concept of an integral. And basically, the idea of a derivative is simply to say we have some sort of relationship, a function, which relates, say, wind to space or pressure to space, wind to time or pressure to time. As we look at a tiny small increment of a change of temperature, for instance, and a tiny small increment of a change of space or a change of time, and we take that in the limit to a very, very small increment, we have fundamentally a derivative. And of course, if we integrate the area underneath this curve, we get something called an integral. Now, in order to predict the weather, we have to be able to take equations that are made up of derivatives and put them on a computer. And the way we do that is to use something called a numerical finite difference approximation, which sounds very complicated. But all it really is our ability to discretely define the derivative of a dependent variable with respect to an independent variable. Once you understand that fundamental concept, you're well on your way to understanding most of the mathematics of predicting the weather. Now, in order to predict the weather, we have to map out space. And we have to map out space relative to the Earth. And what we're going to do here is develop the greatest weather prediction model anybody has ever run in the history of time. Okay? But we have to fundamentally map out where we're going to run our model and how we're going to get our variables into our computer. Well, we start with this very simple spherical Earth. And we carve out a part of that Earth that we want to predict the weather over. And we do this by defining three-dimensional space over a very fixed Cartesian grid. Now, Cartesian represents the very basic representation in calculus of how we map out variables with respect to x space and with respect to y space. Once we have carved out a rectangular part of space, we have to layer several different levels so that we can define the three-dimensional structure of the atmosphere, which is a fluid, which exists over these three dimensions. And what we do, of course, is to define a Cartesian grid, put lots of layers within that Cartesian grid, and that enables us to map out a volume of space over a certain portion of the Earth, and that is where we're going to begin to put our fundamental meteorological variables: pressure, wind, temperature, moisture, etc. Now, of course, one of the more astute people in the audience, I'm sure there are a lot of astute people in our audience today, the first thing they're going to say, wait a minute, the Earth isn't flat, the Earth isn't smooth, the Earth varies. True. There are two fundamental things we have to do when we map out our grid to predict the weather. We have to take into account the fact that the Earth is not flat. It varies quite a bit in terms of the height of the topography relative to sea level. And of course, the second thing we have to do is we have to include some accommodation in our equations for the fact that the Earth is an oblate spheroid, the fact that the Earth is curved. Now, when we think in terms of terrain, we have a very simple way of dealing with terrain in our three-dimensional fluid. what we do is we define a new coordinate system, which we call sigma. It looks like a 6, but it's really a sigma. And what that new coordinate system does, it enables us to map out a coordinate system which follows the structure of the terrain in our model. And it actually follows the contour of the terrain. For instance, here we have longitude running from the western United States over to the east coast. Here's where tide water is. Here's where the Appalachians are, and the front range of the Rocky Mountains. The crosshatch area represents the actual terrain. Notice that each one of these solid black lines represents a terrain-following surface. So when we deal with the real world, we have a vertical coordinate which follows the terrain, and that effect of the terrain gradually damps out with respect to height, topping off at the top of our model. So when we define our weather prediction model, we carve out a volume in space. We let the vertical coordinate that defines where all of our points are that are going to hold our meteorological variables are. We let that follow the terrain itself. So we have a very handy, dandy, three-dimensional volume in space that we will run our weather prediction model over. Now, are you with me? We have a three-dimensional volume in space. We have a variety of weather prediction variables that we're going to store in our model. And this nicely defines, or maybe not so nicely defines, how we're going to store data in our model before we integrate the equations that define the way the atmosphere behaves. Here's our two-dimensional slice in space. Here's x space, y space, and y space. And what we have here are little dots which represent grid points where we're going to store variables at each level in our weather prediction model, starting near the surface and working our way all the way up to 20 kilometers in elevation. Now, what we can do here, and this happens to be an area covering the eastern Great Lakes, what we can do here is actually define the distance between grid points to be as fine as we want. This distance is 127 kilometers. This distance is 32 kilometers. We could go down to 0.3 kilometers, 0.003 kilometers, all the way down until we violate the assumptions in our equations. But what we're going to do is put a grid lattice, a mesh, that's very fine in our model, and we're going to layer this lattice from near the surface all the way up to the top of the atmosphere. So if you can visualize where we're going with our great model, we have a lattice of points that holds meteorological variables. We have several layers in that lattice, and that lattice follows the structure of the terrain. We have three-dimensional space carved out, and all we really need now is to integrate equations that relate what happens in space to what happens in time. So the development of a weather predictional model really starts with mapping out space, mapping out layers in your model, defining the surface of the Earth, and defining the way you're going to store your meteorological variables to predict how they're going to change in time. Remember, when we talked about concepts, we talked about the concept of the predictability of fluid flow and the predictability of the hydrodynamics and thermodynamics of the way fluids behave. We are going to solve those equations to predict the way weather works. All right, I hope I haven't thoroughly confused people and thoroughly put everybody asleep. I see people seem to be awake in the back. That's a good sign. Okay, hooray for the back, right. All right, what I've been talking about for the first 15 minutes, and I hope I've made some sense because the concepts are not as simple as we'd like. I've been talking about mathematics. I've been talking about defining our grid. I've been talking about the fact that we have to understand derivatives, and we have to understand that we integrate equations that have derivatives in time. Before we really go in and set up the equations on our computer to predict the weather, we have to make some assumptions. For instance, how far apart are we going to put our grid points on each one of the levels in our model? How often are we going to solve our equations so that they maintain their mathematical stability. What type of fluid do we have? Is it a fluid that obeys certain laws? What assumptions are we going to have to make about the integrity of the fluid? When will it work? When will our equations work? When will our equations not work? We have to deal with basic assumptions about the fluid and about the way we map out space and time before we go ahead and actually integrate equations that define basic physical processes. Now, when you take a look at this particular diagram, you think this guy is a really sloppy diagram maker. That's what you think, right? The bottom line is that you really get a sense of how difficult it is to forecast the weather because we have to make some incredibly limiting assumptions. Let me give you a few examples. For instance, we assume that the mean resolvable motions dominate within our grid cube. What that simply means is that if we put a grid point every kilometer within our model and 50 meters separated from one another, we have a layer, and then we have another layer, and then we have another layer. In the real world, the fluid is not perfectly homogeneous within that volume. But we have to make the assumption that we start our time integration of the equations with a homogeneous fluid within each cube. Hence, the smaller the cube, the better we define the dynamics of the atmosphere. Now, we have to also make a variety of other assumptions. First of all, we have to make the assumption that the ideal gas law is applicable. Two great scientists, Boyles and Charles, came up with some simple experiments a couple of hundred years ago that define much of the way gases behave. They developed concepts called Boyles and Charles' law. Now, these have to be followed if we're going to be able to integrate our weather prediction model. Another fundamental assumption that we have to make is that when we start integrating our equations, that we start from time equals 0 because we're integrating them out in time and in space. Well, one of the real fallacies about doing this is that we can make the assumption that we perfectly measure pressure, we perfectly measure velocity, we perfectly measure temperature, and that we're not going to have some sort of error when we start out our time integration. This is totally erroneous. We're going to have problems because pressure and wind and temperature do not properly marry to one another. Another fundamental problem we're going to have to deal with is that we have to analyze to get data. We have to analyze data which is very coarse to get data at very, very fine grid intervals. This means that we have to make assumptions about the way data varies over our grid. This is another major liability that we have to deal with. Another fundamental problem we have to deal with is that we have fixed boundaries over this volume. These boundaries are fixed. We somehow have to get information about what goes on around the boundaries. If we cover an area the size of the eastern United States, weather comes in from the south, it comes in from the west, or from the east. So one of the fundamental problems with weather prediction is that we have to define a small volume of fluid with the proper boundary conditions. And they're never perfect. So this is another fundamental liability that we have to deal with in weather prediction. Okay, initial state highly unbalanced. I touched on that. When we start out at time equals 0, we don't know what the exact relationship is between wind and pressure and temperature. So there's some error that's introduced at time equals 0. Another problem the weatherman has to deal with in his great weather prediction model. And we can go on and on and on with problems. One of the fundamental problems is that we use an assumption called bulk microphysics. That's not a video game or something wild and crazy like that. What bulk microphysics is all about, it says that when we have a volume, we have to make an assumption that the rain processes or the snow processes or the hail processes are fundamentally defined by a simple equation. That each raindrop isn't properly modeled, but the bulk effect of all the raindrops, of all the snowflakes, of all the hailstones are properly modeled. And we know that nature doesn't do it that way. But we don't have infinite technology, so we have to make that assumption. Anyway, we're going to define this incredible weather prediction model. And we're going to assume that we have a point with all our variables spaced 1 kilometer apart over most of the eastern United States. we're going to make the assumption that each one of our vertical layers is spaced 50 meters apart. And we're going to go all the way up to 20 kilometers, which is well into the stratosphere. We're also going to have to integrate the equations at 0.1 second time steps for a 24-hour period, which means we have to go through our entire equation set 864,000 times just to make a 24-hour forecast. So what we're going to have to do is model the volume of fluid with incredible precision, starting with our hands tied behind our back because our data isn't perfect and we've had to make all sorts of different assumptions. We're going to cover an area that essentially covers the eastern United States from east of the Mississippi to Tidewater, Virginia on the west and east, to the Gulf of Mexico on the south, to New Jersey on the north, with a model lid at 20 kilometers. That means that we're going to take 1,000 points in X space, 1,000 points in Y space, 400 points in sigma space in the vertical, 400 million points we're going to put in our model, in our computer. So the next fundamental question is, we have space mapped out, we've made all these assumptions, we have all these grid points with all this initial data in there. What equations do we solve to tell you whether it's going to rain in Tidewater in 24 hours? And this is where I have to start to get mechanical and where you all are in a great deal of danger. You might have to duck. Okay, fundamental concepts. There are a few fundamental equations that describe the way the atmosphere functions. And those equations have to define fundamental physical processes that I'm going to try to describe in the next few minutes. Now, I have here a tennis ball. Who would like to catch this tennis ball? Can I have the tennis ball back, please? It's not a souvenir. Throw it back to me. I know you can reach me. I think you can. My fault, my fault. All right. Who knows what fundamental physical process or what fundamental physical concept we just demonstrated by throwing that ball through space? Who has an idea? Come on, you people are supposed to be sharp. I want somebody with an idea. Somebody with an idea. Come on, come on. All right. I'm not hearing anything from anybody. All right. Law of motion is close. I heard momentum. Who said momentum? Raise your hands. All right, you get a gold star. When we threw that ball back to each other, what we essentially demonstrated was the fact that momentum was conserved in the sense that we imparted momentum to that ball by exerting a force per unit mass. If you're talking about a tennis ball or you're talking about the atmosphere, if you're a parcel of air and you're going somewhere and you had momentum imparted to you, unless Newton's laws of motion say unless something else acts to change that momentum, you're going to go and you're going to go and you're going to go and nothing's going to change. But you know that's not realistic because air parcels do all sorts of wild and crazy things. So the first fundamental concept we have to deal with is Newton's second law of motion, which deals with the conservation of momentum. And basically what we do is we take Newton's laws of motion that describe a fluid, sometimes called the Navier-Stokes equations or the Euler equations, and these equations are made up of terms that describe physical processes in the atmosphere. These terms involve derivatives. That's why I had to say at the beginning of the talk, you've got to understand what a derivative is. Now, what fundamental physical processes act on a parcel of air that moves through the atmosphere? All right, we just saw one demonstrated, and that one concept was the idea that momentum can be transported from point A to point B. But there are a lot of processes that act in our atmosphere which change the momentum of parcels. And those processes have to be modeled properly, or we're not going to be able to tell you what the weather's going to be like tomorrow in Tidewater. All right, for instance, when air flows over the surface of the earth, close to the surface, the land is very rough. that rough land acts to drag on the earth, on the air parcel, and it tends to retard it relative to air parcels high above the earth. That's called friction, that's called surface drag. But there's some other forces that are even more important away from the earth that we'll have to describe. Now, how many of you in here have heard of the Coriolis force? That's a fairly large number. Basically, this is the planet Earth. You see the planet Earth? I've got the whole Earth in my hands. I've got my hands over the Soviet Union right now. The Earth rotates. Right. The Earth rotates. Now, because the Earth rotates, it acts to impart a force on air parcels above it. The way it does that, it's a very simple concept, is that if I put my finger right on top of us here in Tidewater, Virginia, and I move my finger away from the surface and I'm an air parcel above the surface, and I realize that the Earth is rotating underneath me, even though there's no direct contact between me and the Earth has moved. So consequently, that parcel of air has been accelerated away from its initial point. That's called the Coriolis force. It acts in the atmosphere, it acts in the oceans, it acts on fluids. And it acts to turn parcels to the right in the northern hemisphere and to the left in the southern hemisphere. That's primarily why the winds prevail from the west in the northern hemisphere and from the east in the southern hemisphere. Now, also, we talked about surface drag, we talked about the Coriolis force. There are other forces that act to change the momentum of a parcel. Turbulence. Whenever we encounter a zone that's well mixed in the atmosphere, parcel momentum can change drastically. But far and away, the most important force is something called the pressure gradient force. And the pressure gradient force, which I will demonstrate in a very crude way in a second, simply says that if there's more mass here, then there's more mass over here. Mass is going to be transferred from one side to the other because the pressure is higher on one side than it is on the other. It's the whole concept of too much mass in X position, too much mass in Y, too little mass in Y position. Mass has to be transferred, and I'll show you an example, this type of thing. This is an aquarium filled with fairly warm water at room temperature. This is juicy juice grape juice, cooled to nearly freezing by little ice cubes. Now, what's going to happen when I pour in the purple juicy juice grape juice? Who knows what's going to happen? That's okay. That's one of the things. Whoever said it's going to sink, it's got one gold star. What about the second thing that's going to happen? It is going to warm up, true, but where is it going to go? It's going to go to the bottom and spread out because it's denser than the fluid that it's next to. If this works, here we go. Yeah, you can see it move. See it move, see it move, see it move. See that purple stuff move? All right, Newton's laws work. Anyway, in the atmosphere, same principle applies. If it's colder here and warmer there, there's a pressure gradient force which changes the momentum on a parcel. Now, we have to view the atmosphere from three-dimensional space. So not only does this occur in a horizontal space, but it occurs in the vertical as well. That's why thunderstorms happen. Thunderstorms happen because of density differences in the vertical. Those density differences, or pressure differences, are set up by horizontal inhomogeneities. So basically, when we look at the vertical structure of the atmosphere, we again have to deal with the pressure gradient force. But in the vertical, we also have to deal with the gravitational attraction, as well as surface drag, the effect of precipitation, the transport of momentum, and turbulence. Now, of course, when we think about a thunderstorm, and we want to predict these with our great model, we have to think about the concept of density differences in the vertical. For example, this is a cork. It is very light. It is not very dense at all. What's going to happen to this cork when I put it in water? I'm going to get my jacket wet is what's going to happen. All right, watch. Okay. You know why it goes up rather than goes down? Right, it has so little density that the water it displaces is sufficient to give it a force that it forces it vertically. This is a rock. It is heavy. Will this same thing happen to the rock? Exactly right. All right. There are a lot of sharp people in the audience today. All right, basically, the whole concept I've demonstrated here is the relationship between pressure gradient force in the vertical and gravity. So that when thunderstorms form, they form because air is heated, it's not dense, and you get eddies going vertically. I'm trying to light a candle, by the way.
Can you push it toward the front of the table because it may be behind the...
This is a candle. This is heat. This is cold. I blow out the candle, and what happens to the smoke? It rises again for the same reason the cork rose, because it is warmer than the surrounding air. It's buoyant. That's why thunderstorms form. If we run our great model, we have to predict thunderstorms, so we have to simulate the equation that describes the acceleration in the vertical, the non-conservation of momentum in the vertical, which is Newton's laws. Another equation we have to put on our computer is something called the ideal gas law, which relates pressure to temperature and density. Thermodynamics. This is living hell in a computer. Do you know what types of thermodynamical processes we have to put in our computer to predict the weather? Quick, somebody, say something about the types of thermodynamic processes. All right, very good. There are people alive out there, that's good to know. We have to take the first law of thermodynamics, and we have to put all these things in our computer. First of all, we have to put the horizontal transport of heat, the vertical transport of heat, and the adiabatic expansion and contraction. Basically, the adiabatic expansion is a concept wherein if a parcel goes up to lower pressure, it expands. If it comes down to higher pressure, it contracts. But that causes a temperature change in our parcel. But getting to things that are easier to relate to, we have to put condensation, evaporation, sublimation, surface heat flux, radiational heat fluxes, and turbulence into our model. Condensation, evaporation, clouds, rain, etc. Sensible heat flux, buoyant parcels coming up from the earth. Radiational heat fluxes, invisible but realistic fluxes, greenhouse warming and cooling right here. And of course, turbulent mixing. Now, to understand how complex this problem is, we have to deal with energy budgets over varying terrain with varying surface characteristics. That means that we actually have to predict the surface temperature to deal with this accurately. That means that we have to calculate the evaporation and condensation near the ground, the sensible heat flux, the effect of radiation downward from the sun, radiation upward from the ground, radiation downward from clouds, and conduction into the soil. You say, that's nice. Is that really messy and difficult? Incredibly messy and difficult. Why is it incredibly messy and difficult? For the following reasons. The time of day, the latitude, and the time of year change the solar angle. The sun is higher in summer than in winter. It's higher. You have a longer period of sunshine during the summer. You have, of course, much more sunshine at the lower latitudes than in the northern latitudes. So you have to include that in your computer. You have to know how much cloudiness there is, because cloudiness affects the amount of sunshine that's down to the surface. Even more complex, you actually have to know how wet the ground is. Because if you don't know how wet the ground is, you can't tell anybody what the evaporation is. And if you can't tell anybody what the evaporation is, you don't know how you can cool the air right above the surface. You have to know how much precip has fallen to do the soil moisture prediction properly. You have to understand drainage, and you have to understand runoff. And this, of course, is a function of the type of surface. The surface over tidewater is different from the surface over Richmond. It's different from the surface over the ocean. It's different from the surface over Tallahassee, Florida, or Montreal, or Baghdad, for that matter. And as a matter of fact, to know the surface, you have to know how much rain has fallen. You have to know what type of soil you've had. You have to know how reflective the ground is, the albedo. You have to know how much biomass there is, vegetation. You have to know the type of vegetation. You have to know the sea surface temperature. And you even have to know the slope and height of the elevation. This equation is pure hell in a computer. But we can't tell you if it's going to rain unless we can simulate this equation properly. Willard Scott talking about all the 100-year-old ladies is not going to solve the problem. This is the problem. Finally, we have an equation for the conservation of mass. We call it the equation of continuity, conservation of gaseous moisture, and the conservation of liquid and frozen water substances. In our great model, we could put 6 or 7 equations for all this in there. We're not going to do it. We're going to put one to make our great model not quite as great. We just put one in there for cloud water, which will tell us if there are clouds and how much precipitation there is. But the point is that to do all of this right enables us to tell you if it's going to rain tomorrow. And if we do it wrong, we've blown it. Okay? Now this is my favorite slide. And if this doesn't get some people's brains working, I don't know what it's going to take. Now, at the beginning of the talk, I said we were going to develop the greatest model in history, and we have. But I said there might be one fundamental glitch or problem with it, or I should have said that if I didn't. Does anybody know what that fundamental problem is with our great model beyond all of the little problems that we've talked about? Very good. You must be a computer expert. You're right on the money. Absolutely. As great as our model is, even with all its limiting assumptions, we still can't run this model to tell you if it's going to rain tomorrow because there hasn't been a computer invented, proven, delivered that can run it fast enough to beat the clock. As a matter of fact, let me give you an idea of how expensive it is to run our great model, even with all its limiting assumptions. If we have 8 equations, 8 dependent variables, and 50 operations per equation, floating point operations they're called, or flops on a computer nowadays, on supercomputers, and if we have 864,000 time steps to do our model, I miscalculated the first time, that's why the green's up there to make it look right. And if we have a matrix of 400 million grid points, it will take approximately 1.37664 times 10 to the 17th floating point operations for a 24-hour forecast. That's a lot of operations. If all 5 billion people in the world were operating on a calculator, they'd have to do billions of operations per person to do this. Now, the only problem with this is that we're making a 24-hour forecast, but it will take, on the fastest computer that weather prediction models are run on, the 6-processor Cray YMP, it will take that machine approximately 2.42 years to make a 24-hour forecast, because that machine can only do about 1.5 times 10 to the 14th operations per day. And that's a very, very fast computer. As a matter of fact, it will do on the order of 1.8 times 10 to the 9th, or almost 2 billion operations when it's running at full efficiency. So here is one more reason why Willard Scott is wrong. Not only does he have models that are imperfect, but even when you make the models almost good enough to accurately predict the weather, we don't have the technology to beat the clock. As a matter of fact, there's almost a 10,000-fold problem here, such that it would take on the order of 885 days to do a 24-hour forecast, which is a bit too slow, even if you can afford to pay the $2,000 it takes per hour to run this machine. Not only do we have a problem with speed, but a problem with memory, because once we've generated all these numbers, we have the fundamental problem of not being able to process them fast enough to turn it into a forecast so that large Willard can get in front of the television and tell you just what the problem is. For instance, if we only store data every hour with 8 dependent variables on all those words, 32 bits per word, we come up with something on the order of 2 times 10 to the 11th bits of data within active memory for every hour of weather processing we do. And if we use a large word, a 64-bit word, we come up with nearly 10 trillion bits of data for data stored every hour. We don't know how to process that to give you the right weather forecast if we could process it fast enough. And of course, what that means is that because we're 10,000 times too expensive, we have to make our weather modeler simpler. Instead of a 1 kilometer grid, we have a 10 kilometer grid. Instead of a 0.1 second time step, we have a 10 seconds time step. Instead of using complex physical approximations, we use simpler physical approximations. So that problem, above all else, limits us. But there are other very basic problems which I'll summarize as I've gone into during the last 40 minutes of this presentation. First of all, we don't have the computer power to make our great model give you the weather forecast that you'd love. Second of all, we have lousy data and very little of it. And I want to dwell on this for just a second or two. The green represents the matrix over which we run our great weather prediction model. The orange represents the great Old Dominion of Virginia. These little X's on the green area represent where we have 12-hour balloon data. Okay? Notice that we have a grid point every 1 kilometer. We have data every 300 to 400 kilometers and every 12 hours. That's terrible data, especially when you consider that you need data over a very fine matrix over short time intervals. This is upper air data. This is getting better, though. New systems are coming on to improve our data, but you can see how crude our data is relative to our model. Here we have surface data, which is somewhat better. We maybe have, instead of 2 stations in Virginia for upper air data, we maybe have something on the order of about 15 surface stations. This is better, and this is hourly data. Now, if we had upper air data like the surface data, we might just have enough data to do it right. Okay, wrapping up some of the fundamental problems. We don't know how to balance the initial data so that the pressure and wind and temperature relate to each other properly, even if we had perfect data. We still have fairly poor surface input data. We don't know how to deal with turbulence near the surface of the Earth within the planetary boundary layer. We haven't derived the mathematics to properly model this yet. Both microphysical assumptions are crude. It means that we don't know how to handle complex interactions between raindrops and snow and ice and cloud water, etc. We don't know how to do the radiation right in the model yet. And what's really interesting is that this great model, much better than any model that can be run in real time, doesn't have any of the nasty greenhouse gases that we're hearing so much about. It doesn't have CO2. It doesn't have the effects of methane or nitrous oxide, which must affect the radiation balance. So we've thrown this out of our model, and we really don't know how to model this properly. We have very bad precipitation data, so it's hard to determine just what the characteristic soil moisture distribution is. And we have a lot of trouble because even if we had a perfect forecast, we couldn't process the data fast enough to give you the details that you need to know to determine whether it's going to rain or not right here in Tidewater or wherever you may happen to be. And finally, in terms of my fundamental talk, I want to show you a quote from a very important man, maybe the most important man some people think in the 20th century. Very few of you have heard of this man, although I hope some of you have. His name is John von Neumann. I think he's one of the most important people in the 20th century. He invented the digital computer. And he came up with this quote long before people were running weather prediction models. And you can read it for yourself. Von Neumann died about 15 or 20 years ago. I'm not sure exactly when. Now, I'm sure you're getting tired and you'd like to cut the talk. If there's some interest, I can show you some examples of weather prediction products that I have with me. I might just add, before I sign off, or before I show you these examples, that in spite of the pessimism of my talk, weather prediction is getting better and better very quickly. And that's because computers are becoming more powerful, and we're learning more about how to model the atmosphere, and we're getting in better data to run our models. So while I've sounded a pessimistic tone, it's because I want you to understand why Willard Scott is not what weather prediction is all about. But on the other hand, we have been able to improve weather prediction drastically with these better weather prediction models, and the future looks very promising. And anybody who's interested in going into this professionally and going to graduate school or college to learn how to do this, I might tell you that the future looks incredibly bright in spite of the difficulties that I've described today. Now, I could show you some more slides of weather prediction products. I'd like to, a show of hands. Would you like to see those, or would you rather just go home and go to sleep and forget it all? Sleep? Okay. Those of you who want to go to sleep, I won't be offended if you leave. Just leave quietly. Just a couple of slides, and I'll let you go. Here's a case study from about 6 or 7 years ago in which a squall line moved through eastern Virginia, produced heavy rain, heavy snow over Washington, D.C. This is a Weather Service radar, and this colored yellow area represents the area of heavy precipitation. Here, of course, is Virginia, Pennsylvania, West Virginia, etc. You can see this nice, narrow squall line. You see this typically when Dr. Dwayne or my buddy Slater shows you all their cute little movable radars. Here's the Weather Service model showing the structure of precipitation. This model was run in real time, and it was a 12-hour forecast. You can see it shows a general blob of precipitation, no nice south elongation, and it shows a maximum over central Pennsylvania. Here's a model run with much more resolution than this. You can see the area of upward motion in yellow, showing a nice elongation, very similar to our observed squall line. Here's a model run with 1/4 of the resolution of this, and you can begin to see some of the mesoscale structure of the vertical motion, which defines where the precipitation is going to be. You compare this, you compare that, you can see that we're moving in the right direction. Notice the mesoscale structure over northeastern Virginia, heaviest precipitation right in here observed. That's where the model has it.
How long did it take to run on the computer those models? Is it different?
Both well,
Take the same amount of time?
no, this model took about 20 minutes of time on a Cyber 205. This model took about 6 hours of time. This took about 24 hours of time. On a Cray YMP, this would take only about 20 minutes.
Do they all get the same input data set?
All exactly the same input data set. The difference is resolution. And here you can see the precipitation, the red indicating the heavy precip. Here's the Weather Service model of 6 years ago. Here's a model with 4 times the resolution and better physics. Here's a model with 16 times the resolution and better physics. This is where all the heavy precipitation was observed in the real world. More interesting diagram, which will only take a minute or two to show, how well the winds can be forecast, even with all the limitations. Here's a forecast, here's an observed analysis of winds and knots at about 1,500 meters above the surface of the Earth. This is observed data, and the barbs represent the direction from which the winds are blowing. Here's a model prediction that we ran about 5 years ago on a Cyber 205 supercomputer. Notice how the observed data, for instance, over Atlantic City right here, you see that nice easterly flow, you see the rapid change to southwest over Norfolk, and strong winds from the southwest over Cape Hatteras. Notice the model showing the easterly winds, there's Atlantic City, showing the hole or weakness in the wind field just north of Norfolk, the southwesterly winds in Norfolk, and then the stronger southwesterly winds near Cape Hatteras. I'll show you a jet stream forecast that's even more exciting. Nope, that's not the jet stream. We'll go all the way up to jet stream level. Right, that is a low-level jet. Is a meteorologist in here? Uh-oh. I'm glad I didn't know that at the start of my talk. All right, here's the upper-level jet, a core over eastern Texas, 170 knots. This is observed. Here you have the Raywinson wind reports. You'll see the strong westerlies across the southern U.S. Look at a tremendous shear where we go from 90 knots or so over Greensboro, North Carolina, right over here, up to like very light southeasterly flow over Pittsburgh and over Dayton. If you're flying an airplane and you don't know this in advance, you're going to lose a lot of fuel if you don't embed yourself in the jet stream. Here's a 12-hour forecast from our mesoscale model, and here's the observations. Note in particular the tremendous wind shear across the state of Virginia. Notice like Hatteras is about 110 knots, Atlantic City up here is about 50 knots. Notice the shear just northwest of Tidewater, and look at the real world. You can see the nice shear across there. It gets even more exciting back here over eastern Tennessee and eastern Kentucky. So the point being is that in spite of all these problems, the atmosphere has a certain structure, a determinism, a predictability to it. As our data gets better, as our computers get more powerful, we'll be able to predict these fine-scale processes and give you more accurate weather forecasts. But it will not happen without stronger, more powerful computers, better data, and theoretical advancements in the science of modeling the atmosphere. So that's basically my presentation for today.